Hello everyone, today we will continue the introduction about the rigid pavement design. Actually, in this lecture, we'll try to finish the rest of the contents about the AASHTO method for the design of the rigid pavements. Here are some typical information required for the rigid pavement design with the AASHTO method. Actually, most of the input information is similar to the flexible pavement design. We need to know the design life of the pavement. Traffic loadings in this case would be the rigid ESALs, reliability, environmental effects, pavement serviceability, material properties, drainage conditions, and load transfer efficiency. Among all those input variables for the rigid pavement design, we need to identify two different variables. That would be the material properties for the subgrade soil, granule subbase, and Portland cement concrete. Also, we have to estimate the load transfer efficiency. In the design of the rigid pavement with the AASHTO method, we first need to specify the analysis period. The table here shows the typical analysis period for different types of the highways. Usually for the high traffic urban highways, the analysis period is around 30 to 50 years. For the high traffic rural highways, the design period is 20 to 50 years. For low traffic urban highways, it's around 15 to 25 years. For low traffic rural highways, it's between 10 and 20 years. This one is pretty similar to the flexible pavement design. In the design, we also need to specify the reliability of the pavement. Actually, there are three variables related to the reliability. The first one is the overall standard deviation SO. The definition of SO is exactly the same to the flexible pavement. The second one, ZR, is the standard normal deviate. It describes the probability that the serviceability will be maintained over the design life of the pavement. And the definition of ZR is also the same to the flexible pavement design. The last one, R, is the reliability we have to use for the design. Typically, we set R as 90% or higher for the major highways and 50% for local roads. Actually, the value of the standard normal deviate, ZR, is related to the reliability specified for the rigid pavement. The table here shows the value of the standard normal deviate applied for each reliability. For 50%, ZR is set as 0, while for 95%, it's set as minus 1.645. The highest value is set as minus 3.75 for the reliability of 99.99%. The table here shows the recommended reliability of the rigid pavement under different road types, including interstate or the highways, principal arterials, collectors, and local roads. And we have the recommended values for the urban and rural areas. Actually, the recommended reliability for the rigid pavement is the same to the flexible pavement. Also, we have the recommended standard deviation for the flexible and rigid pavements. Usually for the rigid pavement, we have the value around 0.3 to 0.4, which would be the value of S0. Also in the design, we have to consider the serviceability loss, delta PSI, which is the difference between the initial serviceability P0 and the terminal serviceability PT. For the rigid pavement, the initial serviceability is set as 4.5 and the terminal serviceability is set as 2.5 for the major roads and 2.0 for the other types of the roads. This one is actually the same to the flexible pavement. Also similar to the flexible pavement design, delta PSI is affected by the traffic loading and climate conditions. In the rigid pavement design, one of the most important steps is to determine the coefficient of the subgrade reaction, which is the property of the subbase and subgrade layers. The page here shows the step to conduct the estimation of the coefficient of the subgrade reaction. First, we have to determine the soil resilience modulus for each season, month, and week. This is actually applied for the subgrade. Then we have to determine the subbase resilient modulus for each season, month, and week. With these two values, we will then estimate the composite K values for each season. Here, K is the coefficient of the subgrade reaction. And then we have to adjust the K value for the rigid foundation and determine the relative damage of each season, month, and week. After that, we will use the average relative damage to identify the weighted K value for the whole year. Finally, we have to apply the loss of the support to correct the estimated K value. Actually, in the rigid pavement design, the subgrade coefficient K, which is the coefficient of the subgrade reaction, is related to the resilient modulus of both subgrade and subbase layers. Also, we know that the resilient modulus varies by seasons, months, so we have to find out the weighted value to identify the effective subgrade coefficient. Now let's first recall the stress analysis of the rigid pavement in the previous lectures. And this analysis can be categorized into two scenarios. In the first scenario, a rigid plate is placed on top of the subgrade directly. With that, we can find out the maximum deflection applied to the subgrade soil. And it's a function of the radius of the rigid plate, the pressure applied to the plate, the elasticity modulus, and the Poisson's ratio. Also, we can identify the coefficient of the subgrade reaction as K equal to Q divided by the maximum deflection, which can be shown in the equation here. If there's one granular base inserted between the rigid plate and the subgrade layer, then we can find out the coefficient of the subgrade reaction as a function of the resilient modulus of the subgrade layer and subbase layer, and also the thickness of the subbase layer. For the first scenario without the subbase layer, we can actually simplify the formula to estimate the subgrade coefficient K. Actually, based on the relationship between the resilient modulus and the modulus of elasticity, we can find out the linear relationship between K and the resilient modulus. If MR is in the unit of megapascal, we will have K equal to 2.03 times MR. If MR is in the unit of PSI, we will have K equal to MR divided by 19.4. If there's a subbase layer between the PCC slab and the subgrade layer, then we have to find out the composite modulus of the subgrade reaction, where K is a function of the resilient modulus of the subgrade soil, the resilient modulus of the subbase material, and the thickness of the subbase layer. We need to use the figures in the next few slides to estimate the composite modulus of the subgrade reaction. The figure in this page can be applied for us to estimate the composite modulus of the subgrade reaction with three input variables: the subgrade resilient modulus, the subbase elastic modulus, and the thickness of the subbase layer. With these three input variables, we can then apply the four subfigures to identify the composite modulus of the subgrade reaction. Also, you have to remember that in these figures, all the units for the MR and E are PSI, and for K is PCI. If you have the unit of the megapascal or millimeters, you have to convert them to PSI or inches. Now let's check one example to see how we can determine the composite K value. Assuming that the thickness of the subbase layer is 6 inches and the resilient modulus of the subbase layer is 20,000 psi, and MR for the subgrade layer is 7,000 psi. We want to find out the composite K values. To solve this problem, we first need to recognize the four subfigures. The first one is the property for the subbase layer. The horizontal axis is the thickness of the subbase layer, and in this figure, each line represents one value of the subbase elastic modulus. The second figure shows the property of the subgrade layer, and the horizontal axis is the thickness of the subbase layer, and in this figure, each line represents the resilient modulus of the subgrade soil. The third figure is the turning point. It will try to alternate the direction of one horizontal line to the vertical line. And the fourth figure is applied for the composite modulus of the subgrade reaction. We need to use the horizontal line from the first figure and the vertical line from the third figure to find out the composite K value. In this example, we know that the thickness of the subbase layer is 6 inches. So we first need to identify the value of 6 inches from the horizontal axis, which would be the first point. And then we have to record the resilient modulus of the subbase layer. That is 20,000 psi. So we have to draw a vertical line starting from the thickness of 6 inches, and then we need to find out the intersection between the vertical line and the one with the resilient modulus of 20,000. In this case, we can find the second point in figure 1. Similarly, by knowing the resilient modulus of the subgrade layer, which is 7,000, we can draw a line, a vertical line downwards, and intersect with the line with the resilient modulus of 7,000. This would be the third point. And next, we will draw a horizontal line starting from point 2, and it will reach to the fourth subfigure. Similarly, for point 3, we will draw a horizontal line, and it will intersect with the turning line in the third subfigure. At the turning point, we will draw a vertical line, and it will extend it to the fourth subfigure. And the intersection between the horizontal line starting from point 2 and the vertical line starting from the turning point will be the point you need to use to identify the composite K value. In the fourth graph, each line actually represents one value of the composite modulus of the subgrade reaction. For this specific example, we will have K composite as 400 psi. So that's the way for us to use the figures to find out the composite K value. Similar to the flexible pavement design, we observe that the modulus of the subgrade reaction also changes over the seasons. In that sense, for the rigid pavement design, we have to adjust the K values for the seasonal variations. And this adjustment will help us to determine the effective modulus of the subgrade reaction, which is an equivalent K value that would result in the same damage from the seasonal values over the whole year. In the adjustment, we define the pavement damage UR as a function of the modulus of the subgrade reaction and the slab thickness. The equation here shows the relationship, and we can use this one to identify the damage in each month, and then use the average damage to find out the value of the effective modulus of the subgrade reaction. We can actually use the equation here or the chart in this page for the estimation of the pavement damage. In this figure, the horizontal axis is the composite K value and the vertical axis is the pavement damage. Also, each line in this figure represents one slab thickness. For example, if we consider the thickness of the PCC slab around 7 inches, we need to choose the line here. And if we are provided with the composite K value of 450 PSI, then the estimated damage will be around 24. So now let's see how we can find out the effective modulus of the subgrade reaction. In the adjustment, we first need to select one D values, and this could be selected based on the typical or recommended D value for the PCC slab. And then we will estimate the composite K value based on the resilient modulus of the subgrade and the subbase layers. And after that, we can use the equation or the chart in the previous page to find out the relative damage UR. With that, we can find out the summation of all the relative damage for the 12 months in the whole year. And then we're going to find out the average relative damage with the value of UR bar. We can then recall the equation here, d to the power of 0.75 minus 0.39 times k to the power of 0.25 to the power of 3.42. By knowing the value of UR bar and the value of d, we can find out the value of k, which would be the effective modulus of the subgrade reaction. In reality, due to the erosion or the mud pumping of the subgrade soils or the differential vertical soil movements, the designed effective K value may not be applied. We may experience some potential loss of the support from the subbase. So we have to consider the loss of the support factor to reduce the effective K values for the design. This table shows some typical ranges of the loss of the support for different types of the materials. For example, for the cement-treated granule base, the loss of the support is around 0 to 1, while for the lime-stabilized material, the loss of the support is around 1 to 3. Usually, the higher loss of the support indicates more reductions of the effective K values. We can actually apply the figure in this page for the correction of the effective modulus of the subgrade reaction with the consideration of loss of support. In this figure, the horizontal axis is the estimated effective K value, and the vertical axis is the corrected effective K value with the consideration of the loss of support. Also in the figure, each line represents one value of the loss of support. For example, if we consider a material with loss of support equal to 1, then we have to choose the second line. And if the estimated effective modulus of the subgrade reaction is 100 PCI, with the correction, we can find out the corrected effective K value as 40 based on the second line. Now we can go back to summarize the procedure for the determination of the K value. First, we have to determine the subgrade resilient modulus for each season month and the subbase resilient modulus. Then we have to determine the composite K value with the chart for each season. After that, we have to adjust the composite K value for the rigid foundation and determine the relative damage of each season, and find out the weighted K value, which is the effective K value. And then based on the type of the material, we need to correct the effective K value with the loss of support. So for now, we have learned all the information we need for the estimation of the rigid ESALs. We have already learned the standard normal deviated ZR, overall standard deviation S0, the slab thickness D, the serviceability loss delta PSI, terminal serviceability PT, modulus of rupture SC, drainage coefficient CD, load transfer coefficient J, modulus of elasticity EC, and modulus of the subgrade reaction. So in this equation, the definitions of the design traffic standard normal deviate, the standard deviation, serviceability loss, and terminal serviceability are all consistent with the flexible pavement design. While in the rigid pavement design, we introduce some additional input variables, including the modulus of the rupture for the concrete slab, joint load transfer coefficient, the drainage coefficient, the modulus of elasticity for the concrete, and modulus of the subgrade reaction. Then we can go through the design procedure defined by the AASHTO method for the flexible pavement design. In this design, we first need to determine the composite effective coefficient of the subgrade reaction, and then we have to select the design serviceability loss and estimate the number of 80 kN equivalent single axial load, which will be ESAL for the design period. And after that, we have to select the level of reliability and overall standard deviation. With this information, we can determine the PCC slab thickness D, and that will be the purpose of the rigid pavement design. The AASHTO method actually provides a design chart for us to estimate the thickness of the PCC slab. In this chart, we will start from the figure on the left, where we will need to know the effective modulus of the subgrade reaction K, which is the corrected effective K value. Also, we have to find out the elastic modulus of the concrete slab to identify which curve in this figure we have to use. For example, if we want to use the third line with the EC as 5 times 10 to the power 6, then we can find one point at the vertical axis, say the point 1. With the point 1, we need to go to check the mean concrete modulus of rupture SC and identify the second point in the scale. By connecting point 1 and 2 and extend this line, we can find out one point at the turning line, that's 3. Also, we will need to use the load transfer coefficient J and find out the value in the second scale as 0.4. Connecting point 3 and 4 and extend this one to the second turning line, we will find the 0.5. After that, we have to check the drainage coefficient CD and find out the value in the third scale, which would be the 6th point we have to use. We will connect point 5 and 6 and then extend this one to the match line, which will give us a 7th point. And at the match line with 0.7, we will also need to check the design serviceability loss and find out the 0.8 in that scale. By connecting 7 and 8, we will find the line will be extended to the vertical axis of this figure, which would be 0.9. And then we will draw a horizontal line in this figure. After that, we will start with another scale that will be the reliability, say it's 0.10. And we need to connect the reliability with the overall standard deviation S0. Say the point is 11. And they will reach to the turning line, and the intersection is 0.12. After that, we have to check the estimated total 18 kilopounds equivalent single axial load ESAL, which will give us the point of 13. by connecting 12 and 13, we will have the line and will be extended to the x-axis of the figure. Say the point is 14. And then we will draw the vertical line, start from 14. The intersection between the horizontal line at point 9 and vertical line at point 14 will be the point we need to use to determine the thickness of the PCC slab. And in this graph, each line represents one thickness. If you find the intersection is between two lines, you need to use the linear interpolation to find out the value of the thickness. Now let's take one example to see how we can use the design chart to find out the thickness of the PCC slab. First, we are provided with the value of the effective K as 22 PCI, and the EC is set as 5 times 10 to the power of 6. SC is set as 650 PSI, J is 3.2, CD is 1.0, delta PSI is 4.2 minus 2.5 as 1.7, and R is set as 95%, S0 is 0.25. The estimated ESAL is 5.1 times 10 to the power 6. And we want to find out the thickness of the PCC slab. Now in the solution, first we need to start with the effective modulus of the subgrade reaction. We know the value of K is set as 72, which is 1 point in the horizontal axis. And then we have to select the curve from this figure. The elastic modulus of the concrete slab is set as 5 times 10 to the power 6 psi, which means we have to choose the third line in this figure. And with the value of the effective K and the value of EC, we can then find out the point at the vertical axis, which is the point 1. And after that, we need to use the mean concrete modulus of rupture SC. In this example, it's set as 650. So we find out the second point 2 in this scale. By extending the line from 1 to 2, we can find out the intersection in the first turning line as point 3. And then we're going to check the load transfer coefficient, which is set as 3.2. You will then find out the point 4 in the second scale, and we will connect 3 and 4 and extend the line to the second turning line, which will be the point 5. And we know the drainage coefficient is set as 1.0. So we find out the sixth line, that is the point 6. Connecting 5 to 6, we will get the line and extend this one to the match line as 0.7. By knowing the 7th point in the match line and the serviceability loss 1.7, we can identify the 8th point, and connecting 0.7 and 8, we can get the 9th point in the vertical axis. Then we will go to the other direction about the reliability. In this example, the reliability is set as 95%. So we have the 10th point, and then we need to connect the 10th point with the value of the standard deviation, which is set as 0.25. We identify the 11th point and then connect 10 and 11 to find out the 12th point in the turning line. And we also need to check the ESAL for the design. Well, we have the ESAL as 5.1 times 10 to the power of 6 in this example. That will give us the 13th point. And then connecting 12 and 13, we will find a line intersect with the horizontal axis as the 14th point. Then by the horizontal line from the 9th point and the vertical line at the 14th point, we can find out the intersection, which will give us the thickness of the PCC slab as D equal to 9 inches. So that's the procedure for us to use the design chart to identify the thickness of the PCC slab for the rigid pavement design. In the rigid pavement design, we also need to use the load equivalency factor LEF for the estimation of the ESAL under the standard 80 kN single axle load. The equation here is applied for us to estimate the LEF, which is a function of the axle type, axle load, and the thickness of the PCC slab. This table shows the typical load equivalency factor for the rigid pavement with the thickness of the PCC slab as 9 inches and the terminal serviceability as 2.5. And you can find out the LEF values for different axle loads and axle types. So in the summary, we can conclude the design procedure for the rigid pavement with the AASHTO method. In this method, we first need to determine the material properties, including the effective resilient modulus and the composite K value. And then we have to select the design serviceability loss. After that, we need to select the level of reliability R and the overall standard deviation S0. For the rigid pavement, it is selected around 0.3 to 0.5. In the fourth step, we have to assume one value of the slab thickness D and use this value to estimate the total number of 80 kN equivalent single axle load ESAL for the design period. And after that, we will use the design chart to determine the concrete slab thickness. If we find that the calculated thickness is close to the assumed thickness, then we can use this value. If the calculated thickness is very different from the assumed thickness, then we have to assume a new thickness and repeat the calculation from 4th step to 5th step until you find these two values are close to each other. The table here shows some typical thickness of the roads in Canada. For the sidewalks, driveways, and parking lots, the typical thickness is around 100 and 125 millimeters. For the street access roads and secondary highways, the thickness is between 150 and 200 millimeters. For the major highways, it's around 200 and 250 millimeters. For the major freeway, it's usually higher than 250 millimeters. The table in this page shows some examples about rigid pavements in Canada. For the Highway 407 in Ontario, it's an joint plain concrete pavement, and the thickness of the PCC slab is 280 millimeters. It also comes with 100 millimeters asphalt treated OGDL and 200 millimeters granule base. For the Highway 104 in Nova Scotia, the pavement is DOUT JPCP, and the thickness of the PCC slab is 250 millimeters. Also, it has a granule base with a thickness around 100 to 300 millimeters. for the auto route 13 in Quebec, the thickness of the PCC slab is 270 millimeters, and it also has a granule base. The thickness of the granule base varies depending on the subgrade soil. So that's all about the lecture today. Thank you very much for your attention. With that, we have finished all the topics in this class. In the next lecture, we will have a review about the final exam.